Namaste. Welcome back to all the faculty members, and namaskaram to Professor Omkar Nath Mohanty ji. Very happy and delighted to have you amongst us, and we are looking forward to listening to you today. So the Vishaya for today has been India's knowledge systems, content, science and technology. Today is day 10 of our faculty development program. And the session now, the Vishaya, the Upavishaya for now, for this session is going to be Dha tuvidya. Before we hand over the session to Professor, we would like to introduce you. I take this opportunity and it's a privilege for me to be introducing you. Professor Omkar Nath Mohanty ji is the Director, Technology and Academic Initiative, RSB Metaltech, RSB Group, Pune. He was the Director and then Chief Research and Development at Tata Steel, Tata Research Professor at IIT Kharagpur, and Vice Chancellor Biju Patnaik University of Technology, Odisha, before taking up the current position in 2010. Was a UNIDO consultant at Harare and Vienna, the chairman of the UK-India Committee on Material Sciences, the Indian coordinator of the Indo-US project on special steels, and a member International Consortium on Ultralight Steel Autobody, ULSAB, and ULSAB AVC programs of the International Iron and Steel Institute. He has published over 130 original research papers, written chapters in several international books. He holds 17 patents. Some of his major recognitions include Fellow of the National Academy of Sciences, National Metallurgists Day NMD Award of the Minister of Steel, Government of India, Materials Research Society of India, MRSI Award, elected a member of the Asia Pacific Academy of Materials, Vishweshwaraya Award of Institute of Engineers in India. Thank you so much, sir. Looking forward to listening to you. We hand over the session to you now. Namaste.
Namaste. Thank you very much. Am I visible to everyone?
Yes, sir. Yes, sir.
Okay. And audible also?
Yes, sir.
Okay. I think it is too bright. Now it should be all right. So first of all, I think I ought to express my gratitude to the organizers of the FDP program on India's knowledge system, and in particular to Professor Richa Chopra ji and my introducer, Professor Anant ji. Is that right? Did I get your name correct? My introducer.
My name is Sri Hari, sir.
Sri Hari ji.
Yes.
My apologies to you.
No worries.
Thank you very much for taking all the trouble of introducing me. And I just wanted to add to that actually I was a teacher, mostly a teacher at IIT Kharagpur, teaching in the metallurgy department for close to 20 years. Anyway, then most important thing is whatever I have done in the past, it's primarily in the area of Dha tuvidya. So I'm glad that today I'm going to share some of what I have done, some of what I have thought about as far as the whole country is concerned on the Dha tuvidya. But we will be confining ourselves to about 45 minutes of lecture, maybe about an hour maximum. And then we have 15-20 minutes of discussion if some of you would like to have some questions on that. So what I will do is, let me start sharing some of the slides. So I will take a minute or two in sharing my slide. So what I will do is share. I don't know if I'm visible now on the slides.
Yes, sir. It is visible.
Okay. So if it's visible, I will try with this. I will try to see if I'm getting the screen somewhat larger than this. But if the screen is visible, then it's fine. I think I don't need to tinker with it and try to do bigger things. Is it all right with all the participants? I must actually address myself also to all the participants who I guess are teachers in various colleges or universities, general or technical and so on. So welcome to this lecture on the India's heritage, Dha tuvidya. So because primarily it is on the ferrous materials, that's what I had said in my lecture, the essence of the lecture, which was sent ahead of time. Hopefully people have seen that. So I'm going to say that the lecture is on the India's heritage in Dha tuvidya. But Dha tuvidya is actually a very wide field. And I'm going to focus on primarily on Damascus swords and the Konark iron beams. And when I say that, obviously, I presume that as far as Damascus swords are concerned, excepting the sword part, the rest of it may not be easily intelligible to everyone present here. So I have a small plan. So India's institution of learning, heritage in science, technology, etc., and the process of making low carbon iron beams of Konark, iron beams, etc. So these we know already. And then India's heritage in science doesn't just or is not limited primarily or only to Dha tuvidya. It goes through several areas, and I would presume that you have gone through some of these lectures. But even then, for the sake of continuity, it would make sense if I just mention here that we are talking of India's contribution or heritage in the area of medicine and surgery, for example, Charaka and Susruta, mathematics and astronomy, Brahmagupta, Aryabhatta. And I'm speaking to you, by the way, from Bhubaneswar, which is the capital of Odisha. And here, not far from here, about 100 kilometers from here, existed in the early 20th century, an astronomer par excellence, that was Samanta Chandrasekhar. Then the universities existed here. About the temples, people would know that Bhubaneswar essentially is a town of temples. Puri is not far from here. Konark, the temple about which we'll be talking, is also not very far. As a matter of fact, it is a triangle. It's a triangle between Bhubaneswar to Puri. We'll see that on the map also. Bhubaneswar to Puri and Puri to Konark, it is a triangle. And Puri and Konark, both of them are on the coast of the Bay of Bengal. Then I will not talk about the other metals. So we will skip that today. I want to tell you something which should make all of us proud. And this is about the Industrial Revolution. Now, all of us, we know, we read it in the books of science, history of technology, that the Industrial Revolution took place in Europe. And it took place actually in stages. So in stage one, when the steam engine started, and subsequently electricity also started, and so on and so forth, and that everything took place primarily in Europe. That's what people believe. But here is a scientist from Europe, from England to be precise, and he is Colonel James Todd. He is from the British Museum. The awardee is British Museum's Dr. Paul Craddock, but the award is called the Colonel James Todd Award. And the James Todd Award is a very famous award given away to somebody living outside India, but who has contributed a great deal either to India's philosophy, India's living, India's science, India's technology, and he is given the Colonel James Todd Award. So I'm not going to speak about James Todd. He's a very well-known Indologist working on Indian science and technology. But that happened close to 60 years, 70 years. So this year, 2019, not this year, 2 years back, it was awarded to a noted scientist from the British Museum, Dr. Paul Craddock by name. Now, interestingly, what Dr. Paul Craddock said, and this is, yes, something more also I must tell you. This is the Rana of Mewar. So the Maharana Arvind Singh of Mewar is shown here, or seen here. You can see the first person. And then his son is Lakhyaraj from the same family. is his son and the Sian. And this is the awardee of 2019. And this is a photograph you are all familiar with, or mostly familiar with. He is primarily the author of NEP, the new education policy or the national education policy of India, which was accepted by the Parliament in the year 2020. So today we all know and talk about the NEP, and the authority on that and the author of that book or the document is no other than Dr. K. Kasturirangan, who was once upon a time the chairman of the Indian Space Research Organization. So Kasturirangan is the chief guest on that occasion, so he is also shown here. Now, what did this gentleman Paul Caddock say? This is very interesting. First of all, I must say the Maharana of Mewar Charitable Foundation of MCF, it recognized service, etc., nation building, and they have already awarded 37 up to 2019. So now that means it is close to 40 awards which have been awarded, and the foundation has instituted as many as 13 awards, which are called the Colonel James Todd Award, one of them, and it recognizes foreign nationals, as I have said, in order to recognize the spirit and value of Mewar. So Paul Craddock is a scientist attached to the British Museum. Now, interestingly, Paul Craddock has been studying early metallurgy in India, especially in the Jawar region and the mining township about 40 kilometers from Udaipur. And this Jawar, some of you would know, all others will not know. So I will spend a minute on that. But I will also tell you that the Paul Craddock Award is a James Todd Award, sorry, pardon me. Paul Craddock is the awardee. The James Todd Award has previously been awarded to the great journalist Mark Tully, the British journalist, but who has become Indian now, and the author Nobel laureate V.S. Naipaul, not of Indian origin, but India connections he had. He was actually primarily from West Indies, and who breathed his last about 2 years back. So they were the previous award winners. Now, why am I mentioning all that in great detail? Essentially because of the fact that Craddock, Paul Craddock, what did he say? He said the following. Paul Craddock says that the Industrial Revolution actually took place here. I don't have to go through what he said in great detail. Suffice it to say that although he is a British technologist, and the 17th century or early 18th century Industrial Revolution, when it was taking place in Europe, he is telling that the Industrial Revolution took place in India. Why did he say so? He said so essentially because in the Jawar area where he was working, the Jawar area, it is now almost established that zinc metallurgy, I repeat, the zinc metallurgy started in India. And if you say that the zinc metallurgy started in India, what is so great about zinc? Well, it's a low melting point constituent or metal, close to 330 degrees or 327 degrees. But what's so great about it? The interesting aspect is the melting point and the vaporization temperature, they are not very far from each other in the case of zinc. So when you start the standard processes, you take the mineral, produce the salt, and then evaporate it, condense it, you get a metal. But here, when you start evaporating it, or when you start melting it in order to produce the metal, it also starts evaporating, which means it will evaporate away, it will go away. And it's very difficult, therefore, to collect the metal. The Indians, the kind of furnace which they used, and Paul Craddock worked on the Jawar mines for 30 years, they produced a very innovative, ingenious technique in which the furnace was actually facing downwards, so that as soon as the vapor will take place, it will actually go downwards and it will condense there instead of going upwards and getting lost. A very ingenious technique. So Paul Craddock therefore said that the Industrial Revolution started here. Now, this makes you feel as an Indian really proud that we had this kind of metallurgy, and even iron metallurgy. Previously, people were thinking that the iron metallurgy, perhaps in Africa, it started about, let's say, 2,500, 3,000 years back. Now in India also, there are areas where the iron metallurgy is as old. That's what people say. Okay, so much then about the Paul Craddock story. As far as the astronomy is concerned, I told you that not far from here was a great astronomer from a remote village, which is about 90 kilometers from Bhubaneswar. And his name was Samanta Chandrasekhar, because he fabricated the most ingenious instruments out of wooden sticks and bamboo chips. No telescope in the modern sense. This is the beauty. And if there is no telescope, in spite of that, when he wrote these 2,500 slokas, actually it is 2,501 slokas. And this work was highly acclaimed by the Western press in 1899. How was it acclaimed? Because a professor from Ravenshaw College, which is now Ravenshaw University, he went to, he didn't go, he actually translated the work of Mr. Chandrasekhar or Samanta Chandrasekhar, and he translated that into English. And his name is Professor Jogesh Chandra Rai, who was teaching physics and also biological sciences. And he went to that village and he was amazed to see this simple rustic person related to the local king and who had written these astronomical treatise. It was 2,500 slokas it had. Subsequently added one after 2 years, so 2,501 slokas. And the gist of that was translated to English, and it was sent to Royal Society. And what did the Royal Society say? The Royal Society said that not only is his discovery about particularly transit of Venus, not only is it as good as any in the world, but they compared it to Jeremiah Horrocks, who is considered to be the most important astronomer in the world ever existing, who actually was an English astronomer somewhere around Lancashire. He existed in the 17th century, and he also worked on the transit of Venus, and he also worked on how the Venus is expanding and the Saturn is actually contracting or shrinking, all that Jeremiah Horrocks discovered. And Royal Society in England compared this man Samanta Chandrasekhar to Jeremiah Horrocks. In honor of that, the Indian government actually introduced a stamp in honor of Samanta Chandrasekhar. So that is the kind of contribution as far as Indian astronomers are concerned. There are others. We don't have the scope to talk about Aryabhatta, Baramihira, and so on, but we all know, and Sushruta and Charaka in the medicinal area. So let's switch now to evolution of materials in society. Now, as far as materials are concerned, the Stone Age, so man came to the earth in 1 million years in BC. That, of course, we know. But then the Stone Age started, and the Stone Age was more than 10,000 BC. But then the Chalcolithic age started. The name Chalcolithic age tells us that native copper started much before iron started. So the copper started, and the smelting of copper also from malachite started 6,500 BC, etc., etc. And the bronze, which is copper tin. But actually, we must correct it. It is not copper tin bronze that started in India. It was there are 2 or 3 other elements, and mostly the tin part came much later. And the first bronze that started in India is copper with arsenic. So the arsenic bronze, which was an accidental alloy. Why? Because most of the copper mines, the malachite and so on, they contain also a little bit of arsenic. So our ancestors did not know that it is an alloy of copper and arsenic, but they found that it is much stronger than the pure copper, and they stuck to that. So the bronze actually became very important, but little did they know that this is actually toxic or carcinogenic, and which is why later on the arsenic part was substituted by tin. So today, of course, we know copper tin is the real bronze. In between, the silver also started, and people started adding silver to bronze, as well as silver also as a native metal. So the Bronze Age included the copper arsenic, copper tin, copper silver, and the first man-made iron object started about 2,900 years BC. And when I went to Giza in Egypt, that happened about 2 years back, the first man-made iron objects in the Great Pyramid of Giza, which is 2900 BC. The interesting aspect is Giza is close to Cairo, but about 100 kilometers north of that, very close to Alexandria, you will find the other pyramids, and they are 4000 to 4500 BC. And they would say that Giza pyramid is a young boy, but actually Giza pyramid itself is close to 3000 BC. If you say 3000 BC, that means you are talking of 5000 years from today and back. So the meteorite started, then lead started, and then actual tin, the ores of tin started, etc., etc. Then when we come to the BC 200, cast irons in China started, and we had not started the cast iron yet, but the Indian smelting, it started around 500 BC, but the smelting, we did not know how to melt it. Melt what? Melt iron. 1539 is the melting point of iron. You must add another 60 degrees in order to make it very fluid. So you are talking of 1600 degrees centigrade is what the container has to withstand. And we didn't have in India the container that could actually withstand the high temperature of 1600 or 1650 degrees, which you call the refractoriness, which is why you couldn't melt. But we will soon discover that although we didn't melt iron, we knew how to make excellent iron. So iron, cast iron, etc., started, and the Delhi iron pillar, which all of us we know about, and unfortunately today we will not be talking about Delhi iron pillar. Suffice it to say that Delhi iron pillar was about 356-400 AD. But even then, the 400 AD essentially means 1600 years back. 1600 years back, the Delhi iron pillar was made. But it was not made in Delhi. It was actually in Madhya Pradesh. And from there, it was brought sometime in the 14th century AD. Another day, maybe we'll talk about the Delhi iron pillar and why Delhi iron pillar is famous across the globe, because it has remained rustless over the 1600 years. So therefore, we have a book by Professor Anantharaman, which says or talks about the rustless wonder that India was about the Delhi iron pillar. But there are other iron pillars like Dhar iron pillar, Mandu iron pillar, and the Dhar, Mandu. Dhar is actually even larger than the Delhi iron pillar, but came much later, 1700 years, 700 years later, etc., etc. So the iron pillars were there. So we talked about the zinc smelting, started in 1200 AD. Then the blast furnace, Bessemer steel, they came much later. The Indian steel, etc., started. We started the LD process of modern iron making in Rourkela steel plant in Orissa sometime in 1950s. So, so much then about the iron making, or the iron making to iron to steel making. But interestingly, if I were to draw a graph between the relative importance and the intensity of use, is this visible? Is the slide visible? Can some of the participants tell me? It's slightly faint, but is it visible? Hello. Okay.
Yes, Professor.
Yes. Okay. I was asking if the slide is fully visible or not.
Yes, it is visible.
Okay. Wonderful. So therefore, what I was trying to say is that the intensity and of the use of the materials, that's very important. For example, earlier on, if you're talking of 10,000 BC, then that's where the copper age started. Gold and copper, they're very important. Then, of course, the bronze became important. Subsequently, iron, cast iron, steels came therefore sometime later, around 1800. Then the alloy steels came, light alloys or aluminum and so on, super alloys, titanium alloys. So they became more and more important in different era. That's what the diagram shows. But as you go along the years, then you will see polymers, elastomers, composite materials. They would become extremely important because many of them are lighter, particularly composite materials. All aircrafts are made of the carbon composites today. Not all, the defense aircrafts. And the other aircrafts are primarily made with aluminum, and the Russians make some of their aircrafts in titanium. When you come to iron age, iron primarily, people knew about iron. Our ancestors knew about iron from the meteorites. And in the meteorites, you'll find the irons were there, and man saw the iron from the meteorites for the first time. Subsequently, of course, the iron ores, etc., were there. And since we are not sitting in a class of all the sources of iron, suffice it to say that the common ores of iron are hematitic, which is iron oxide; magnetite, it is Fe3O4, whereas hematite is Fe2O3. And therefore, if you are talking of the iron content, then it will actually vary between these kinds of ores. Hematite is 2/3 is the iron content, magnetite is 3/4. So you will find more of iron is there. But if you can also have goethite, in which there will be water along with the iron ore, and the limonite, so more water and so on. So the Earth's mantle is also said to consist of large amounts of iron compounds in the form of iron and magnesium alloys. So etc., etc. We'll not go further on that. So the meteoric irons, interestingly, in some of the museums, you'll find the meteorites also. And you'll find that some of the meteorites came in the Cape of York in northern Greenland. And these are primarily siderite. And they are found today, as I said, in New York Museum, for example, in New York Museum, where they are called the Omen, which weighs about 3 tons, and the tent, which is weighing about 30 tons, and the dog weighing about 0.4 tons. So these are the names of meteorites. And how do the meteorites look in the microstructure? The metallurgists like me, we would call it Widmann-Starten, which is primarily needle-like structure. And we all presume that the needle-like structure in the meteorites happened because the meteorites that we found in Greenland and in a few other places in the world is essentially because the meteorites flew from the outer sky, from the meteorites through the atmosphere of the Earth and then onto the Earth's surface. In the process, naturally, when they were red hot due to the friction, and they get cooled at a very fast rate when they fall on the surface of the Earth, and the cooling rate when it is high, you get the needle-like structure here. And this is at higher magnification, the same thing. The timelines of just iron and steel industry, if we talk of, and say that 1100 BC, now it has been corrected. 1100 BC, no, it has to be read as 1800 BC to 2000 BC. And in addition to Karnataka, now in many parts, some parts of Uttar Pradesh, also the iron manufacturing areas have been found out. So we will not go through the entire listing because we must go slightly faster than what I have done so far. This is only to show that not only was iron being manufactured here, but it was being also transacted as a commodity. So therefore, you will find here that the Delhi iron pillar was actually manufactured during the Gupta period, which is around 400 or 396. And then it was later moved to or shifted to Delhi. And this is roughly 16 meters tall and close to 6.5 tons high. But the iron that we find or will discuss about, the Konark Temple, came much later in the 13th century AD, etc., etc. It goes on and on until we come to the first steel plants in India. And the first steel plant was the Bengal Iron Works in Kulti, not very far from Kolkata. And then, of course, the Tata Iron and Steel in Jamshedpur, 1907. Then the other steel plant that came, Steel Authority of India Limited, formed in 1978. But before that, Hindustan Steel, which is the precursor of the Steel Authority. Vizag Steel is also there, 1990. Acquisition of overseas steel plants by Tata Steel, overseas steel plants by Mittal. Mittals took over Arcelor, and Tata's took over a huge steel plant called the Chorus, etc., etc. happened. So today, India is a big place for steel making. Although China is #1, India is a distant second. So while India produces roughly 120 million tons, China produces about 950 million tons. The world produces close to 1900 million tons. So 50% of what the world produces is produced in China alone. but India is also very important. And this is a slide I thought I would share with you just to show that even in the Vedic period, this is actually the Hindi translation of one of the shlokas from the Rig Veda, and it talks of how iron used to be made. And you will find here how initially the iron used to be made and how they were adding carbon to that, and what was the carbon made of. So you can see here, lakdi ke tukde ke saath tapane se jali hui lakdi ka koila. So they knew how to add carbon into the iron oxide in order to produce iron. So this is quite important that our people knew, but this is the Hindi translation of the Sanskrit version of the making of iron or the process of making iron. And another evidence to show that India knew exactly what was happening in the ferrous metallurgical area. And this is an example essentially because we find here that the kinds of loha, today if you ask a metallurgist, he will not take long time just to show from very soft iron to permanent magnet, which is high carbon. So from Bharmaka to Chumbaka to Karsara to etc. to Romaka. Romaka is the permanent magnet. Whereas in this is the magnet soft iron part, low carbon steel. But when you come to the carbon steel, this is all low carbon. That means lower than 0.2, 0.25, etc. But when you come to carbon steels and go on the carbon axis, that means go on increasing, then you'll find Khara is the carbon. But if you go to Sara, more carbon, then Hamala, more carbon, etc. Even more carbon than Bajra, then Kala. And this develops a hard cutting edge that our ancestors knew. Then we talk of cast iron, and from which the kadais are made. All of you are fully familiar with the kadais. And this is again known as the Mridu cast iron or the Munda Loha. Munda Loha is cast iron. Tikna Loha is carbon steel. Kanta Loha is soft iron. So this is very important. So Loha itself used to be known as Kanta Loha, Tikna Loha, Munda Loha. Then the tradition in making iron, as I said, from the BC era till today, it has actually moved. But most important from this slide, I would like all of you to know the first irons which are made in the furnaces in India. This is the iron making is not very different from the iron making in other places. It's called Bloomery Iron. And the Bloomery Iron, how it is processed is this. The Bloomery process is you first of all mix the fragmented iron ore and make them smaller and smaller. And then you add charcoal. Why charcoal? Essentially because charcoal means it contains carbon and the iron oxides are the ores. So you have to take the oxygen out, and you can take oxygen out if you add carbon, because the carbon has a stronger affinity for oxygen. So the carbon will take the oxygen out. But in the process, in the blast furnace where this takes place, that the carbon takes away the oxygen. But in the process, the blast furnace iron becomes very rich in carbon. And therefore, you have to once again remove the carbon in the steel making furnace in the modern processes. But in the Bloomery processes, what were they making is something described here. Fragmented iron ore, charcoal. You mix them together and don't take it to 1600 or 1650 degrees centigrade, because we did not have the container. So what happened was they mixed the charcoal with iron. Our ancestors knew that the iron ore contains not only iron oxide, it contains other oxides such as manganese oxide, aluminum oxide, silicon oxide. Silicon oxide is nothing but silica, which is sand, so to say. So you must have found a lot of sand in most of the ores. So therefore, alumina, silica, and the manganese oxides, they're all there. And all these oxides put together, if you put them together, they are not what we require. Therefore, we don't need to get them in the native form. They are still in the oxide form. We need to selectively take oxygen away from iron oxide. So what will happen to the other oxides? They are still there. So the other oxides, when they are together, they are all together, their melting point becomes lower. And when their melting point is lower, how low? around 1150 to 1200 degrees centigrade, all these oxides, they melt, become liquid, and we call that this becomes a mix of solid and liquid. Why solid? I will pause for half a minute so that you will think. Why solid? Because we have just now discussed a minute back that the melting point of iron is very high. So when iron oxide is reduced by carbon, that reduced means that carbon has taken away the oxygen, which means from the iron oxide, what has remained is pure iron. And the pure iron melting point is 1539, and it is not molten yet. So therefore, it is still solid. So the iron part is solid. What about the other oxides like silicon oxide, aluminum oxide, manganese oxides, and so on? Now, these oxides have remained as it is, but their combinations together with carbon has melted them. So now you have the solid iron, which is what is reduced from iron oxide. It has now been devoid of its oxygen, which has been given away to carbon. So what remains is iron, which is solid, and the oxides, mixture of oxides, which is liquid. So you have a solid and you have a liquid. They are all mixed together, intimately mixed. So now what you do is we start hammering them. When you start hammering them, you expel actually the liquid slag by hammering. And what remains is primarily pure iron because you are hammering it. So it's called wrought iron, WROUGHT, which is worked iron. And this piece, what remains is actually low carbon iron. So the liquid part is thrown out or expelled by the hammering process, and what remains is the solid iron. Let's see the process now. So this is how the Bloomery furnaces were looking like. In many parts of India, you'll find remnants of Bloomery processes. They're made of clay and thatched clay with some of the stones, and the chimney is there. And from the bottom, in some cases, you'll find the blowers, but the Indian original ones, they didn't have the bellows. So there are excellent U-tube pieces. You will find them African iron making, Indian iron making, European iron making. And I recommend to the participants here, you kindly go through some of these U-tubes of Bloomery iron making in different parts of the world. And you'll find how interesting they are because they are slightly different from each other. Then once from this process, the iron comes out, actually, as I said, it becomes a semi-solid mix. The semi-solid mix now that comes out from here is now hammered by this hammer. When you hammer it, the iron bloom, which has been just removed from the furnace. So now the surrounding it are pieces of slag. Those of you who come close to Jamshedpur, I have seen that near Ghatsila, which is about 50 kilometers from Jamshedpur. And from the town of Ghatsila, you go 12 to 14 kilometers, you will find ancient iron making places. And you can make that out by the nuggets of slag which surround the iron making space. The iron has been removed, but the slag still is there. Now, in addition to that, in many parts of India, and particularly in Kerala, and also in Odisha, in many parts in Koraput, and in Jharkhand, you'll find the ancient iron making furnaces like the Bloomery furnace still existing. Just 1 second. And you'll find once the weapons are made from the iron, they look crude here. In some cases, they look more crude, but in some cases, they are fine. It all depends on how much of impurities are there. Although, what happened? Although we are actually making it pure iron, we say, the iron-wise it is pure, but it still contains some of the slag entrapments. No matter what you try with the hammering, you'll find that the entrapment of some of the slags, they are still embedded. Okay, so we'll now come to our major topic, examples of metallic products in ancient India. Just a few examples, just one most important example perhaps, and we'll talk of the Nataraja. of Tamil Nadu area or southern part of India. So this is the dancing Shiva, and this Nataraja is made of, this is primarily in the gallery, in the Chola bronze in the Tanjavur Art Gallery, but you'll find similar Natarajas, beautiful Natarajas elsewhere also in the world, taken from India. So with that, I come to India's heritage in iron technology, the part 2 part, because from the general process of iron making, we come to what is called the Damascus swords. On the Damascus sword, the first thing that takes place is the crucible steel process, because Damascus swords are made from high carbon steels. I told you about a minute back that the steel that is produced through Bloomery Iron is low carbon. So one has to produce, first of all, with steel, which is the high carbon steel. And then from there, the Damascus swords are made through a forging process. And the forging process that takes place for making swords, both the material and also the processing of the material woods to the product, which is Damascus swords, which could be as long as 3 to 4 feet also. It is absolutely fascinating how the new materials or these high carbon materials are produced and how they were forged into the Damascus swords. And the reason is the following. Primarily, the high carbon material is brittle. So the material which is brittle, how do you convert that into a thin sword? Secondly, even if it has been converted somehow at high temperature, at room temperature, the swords are wielded by a soldier. And just to highlight the point, those of you who are aware of how a kodai behaves, if I take a cast iron kodai, let it fall from a height of 3 feet to 4 feet, it will actually get fragmented into pieces. How is it that almost of the same composition, our ancestors could make extremely thin materials, roll them or forge them, and these swords were operating in the battlefield, because when you wield a sword, it will bend, but it still doesn't break. Whereas a kodai breaks of the same composition. This is what we'll talk about. Secondly, you will find it also had swirling patterns, these swords. So we'll soon see. So it's a remarkable steel, legendary steel, etc. But we will not talk about the all details. So it has optimum structure and property. And this is one interesting point I must say. If you travel from, for example, if you travel from Bangalore to Mysore, so Bangalore to Bangalore to Mysore, when you travel, then you'll find Tipu Sultan's port also. And both in Hyderabad's armory of Golconda and Hyderabad's Nizam's place, and Tipu Sultan's armory, Ranjit Singh's armory in Tanjavur, etc., etc. Maratha armory, you'll find a number of these swords. Not just that, in as many as 50 to 60 museums around the globe, you'll find in New York, in Frankfurt, and elsewhere, UK in many places, the Damascus swords. Now, the British were so scared of the remarkably sharp and effectiveness of the swords by the Indian Sepoys in the mutiny of 1857 that they decided to destroy them. And once the mutiny was quelled, and they had to bring a special machine from London to actually destroy some of the swords. How do the swords look like? Now, this is a typical sword. You see here how beautiful the sword is, very long, and this is the ornated cover, of course. So this is a different thing. We'll not talk about this, but we'll talk more about the sword part. And the broad observations on the swords, 2 categories of Damascus opens. One, the pattern welded Damascus, and the other, true Damascus. Both types, they reveal several attractive surface patterns. But the layered surface patterns which we find, which are actually layer and layer and layer from low carbon to high carbon, they are essentially Damascene materials which you find mostly in Japan. And they are not a single steel. They are multiple steels, one above the other. They are forged together and patterns are wielded out of that. So multiple steels folded and forged. Whereas what we talk about, the true Damascus sword, which is also called the wood steel. This is primarily the same steel, not the layered steel. Now, how do they make the high carbon steel so thin? So Damascus Sword with English translations, you'll find some of the swords here. I think I forgot to mention one very interesting point here. The interesting point is that the photograph here, I should have explained. The photograph, why I should have explained, is because of the fact that in this photograph, you are able to see two kings. I don't even have to tell you that on our left, we are beholding the picture here. So on our left is a person with a headgear. And with this headgear, it is not very difficult for you to recognize the person. He must be a Greek, and it is actually Alexander the Great. And on your right is actually the Indian king, Puru, from the Punjab. Now, Puru was defeated, and the Greek emperor, the great Alexander the Great, was the conqueror of Puru. This is known in history. But this is a very interesting imagination of an artist, just to highlight the fact how strong India was on technology, that it is as if to say, Puru is telling Alexander, you may have won on the battlefield, but I have a superior technology to offer to you, which you may not be aware of at all. So therefore, the vanquished king, Puru, is making on a platter some special materials, as if to explain to him that look here what I have on my right hand and on the left hand on the platter. They are very special materials. They are wood steel. So, so the wood steel is the starting material for such kinds of swords. So there are two things I have said. One is the swords, which are very sharp, and they remain sharp for long battles, and also they remain sharp over long period. And most important, their length is quite high, and they are quite thin, in spite of the fact, or notwithstanding the fact, that they are basically high carbon. So how is it possible? High carbon material, 1.3, 1.4% carbon, and close to cast iron, 1.5 also some of them, and yet they are quite ductile in order to work as or function as swords. Second thing is, they had very special patterns on the this kind of patterns. Multiple, of course, this is from multiple steel, but I will show to you, yes, this is a typical Damascus sword, but you can see the patterns. And these patterns, they look like swirlings on a textile body. That means if you take a piece of cloth, let it fly in air, then you'll find there are waves, as if waves are there. That's what we call as swirling patterns. And these swirling patterns in English are also known as damask, D-A-M-A-S-K. And D-A-M-A-S-K, they are known as the damask, or these kinds of patterns which I have now magnified. So the wood steel is a very special material. I will not, yes, I think I will skip over some of these. The wood steel, when we are talking about, these are advanced materials with very high carbon, and they are produced by the same what you call process of making low carbon in the Bloomery iron, but you have to add carbon by some process, because I have just now told you that the Bloomery iron produces less than 0.1% carbon. But here we are talking about 1.3, 1.4%. So how do you add carbon? Now you can add carbon to the low carbon material, which is wrought iron, or you can take a cast iron, which is like 3.5 to 4% carbon, and remove carbon. Both processes have now been discovered in India and elsewhere in the world also. This is a point I want you to carry home. One is Bloomery process of iron making, I have just now said, it contains only low carbon. If it contains low carbon, in order to convert that into crucible steel, which is a wood steel, we call it, also another name of that is crucible steel, we add carbon to the low carbon material. The other way out is actually primarily removing carbon from the pig iron. Pig iron is iron which is produced in blast furnace or any process where cast iron is produced by adding lot of carbon to the extent of, let's say, close to 3.54%. So if you have 3.5 to 4%, the material is very brittle. So it has to be, you have to remove some of the carbon. Either way, you can produce the woods. Let's see the first process now. The first process is the carburizing process of the low carbon material. So we have just now seen that the iron ore and the charcoal, they are mixed together inside the furnace, and this is a bellow. The bellow may or may not be there. This is only to pump in air into the furnace, cross section of which is shown here. This is a Bloomery furnace. We are talking of 1200 degrees centigrade, not 1600 or 1650 degrees centigrade. It's only 1200 where all that mixture is made. And now you put it into this furnace, and we produce a sponge iron, which is the low carbon material. And now inside the crucible, we add charcoal to it. So the low carbon material is produced here and it is charged into the crucible, and the charcoal is also added, which is coal, and you shut it. The crucible now is closed, and put the crucible now into the furnace, and it will actually contain high carbon now once you hold it at 1200 degrees centigrade for long hours. So you have what you call a woods material, and this woods material now once again is heat treated in the process of what we call the forging process. And so the woods material or the pellets, they are charged into somewhere between 650 to 850 degrees centigrade, heat them, and then they are brought out, and then the hammering is done, and you produce a hardened blade. But this blade has to be once again heated and quenched in order to produce what is called a sharp edge martensite, which is a phase transformation. The history is very interesting. We don't have time to go through the history of the Damascus swords. Suffice it to say, during the Crusades also, Europeans started using it. Obviously, when you call it Damascus swords, the name Damascus also suggests to you that the capital of Syria, today's Syria, which is called Damascus, which was also a great city of trade and commerce. And that's where it was being freely traded. So these woods metal used to go there, rest of the world used to purchase, and then the technology of making the blade or the sword blade was also gradually spread, and people started purchasing it. So that is another reason why it is called Damascus swords, because people started buying and selling it in the Damascus market. So the most important thing is, we at the National Metallurgical Laboratory, where I spent 11 years as a director of the National Metallurgical Lab, which is a part of Government of India's CSIR, we produced by a special process. This is how the as-cast material is, which is elongated, very brittle, but by hot and warm working, we produced mechanically worked material, extremely fine precipitates, and the analysis of my grain structure shows that it is 10 microns and less. It's a two-phase mixture, and in electron microscope, we saw the microscopic character. We found there is a white phase and there is a dark phase. The dark phase is the carbide, and carbide, which is very fine, which is only a few nanometers, and you will find that the two phases, one hard, one soft, they will give you the superplasticity or very good ductility. And when this work was going on, I was at Jamshedpur at the National Metallurgical Lab, and then I was interacting with Stanford University's Professor Sharby, SHERBY, a short for Sharbikov from Russia. Perhaps he must have come and settled down in USA in Stanford University. So Professor Oleg Sharby, he produced, give me half a second. Hello. I am in a meeting. I will come back to you. So he was the first to write an article on the Damascus Swords revisited, and that is how I was myself interested. And we found that this kind of blades are possible. But when we produced this material at NML Jamshedpur, then Professor Sarvi's article also was published, and the work of not Sarvi's article was already existing, but this is the Scientific American front, the cover page. It showed Damascus Swords demystified. That's what Professor Verhoeven from Iowa State University in US, he actually did a lot of work, and you'll find an excellent YouTube piece by Professor Verhoeven. It's called Wood, Steel and Sword Making. Those of you who are interested, you can go through. The interesting aspect is, those of us who are metallurgists, you are not required to know about this, that there is something called strain rate sensitivity. If that is quite high, then the material behaves as a superplasticity. And this is the beauty of the entire material. And you'll find at a certain temperature, you have to process it, you have to produce fine grain size, two phases must mix together, then you get actually the extremely high, what you call, deformation. We got as much as 500% deformation, and it was established that in the iron carbon system, which is called steel, up to this point, that is 2% or 1.8%, it is steel. Beyond that, it is cast iron. But the process is that because of the two-phase mixtures and extremely fine two-phase mixture, you can get the ductility. So the most important thing I didn't tell you, and that is at the NML Jamshedpur, we produced the fine grain size, we produced the ductility, but we could not produce the pattern. And the pattern came from Professor Verhoeven's work, and he proved and showed that that happened because on a particular day, he called it is an act of serendipity. Why act of serendipity? Because on a particular day, he did not have enough materials. So he had some sand taken from the Karnataka beach in USA. He was making the steel. He put that sand into the molten material. Lo and behold, he got some carbides here. This is how the fine carbides look. And if you hammer it, then he got the excellent patterns. So he essentially declared that you need vanadium carbide or tungsten carbide, which are very strong carbide formers in the microstructure, in order to produce the patterns. And this is what you find in the YouTube. So the entire process of making extremely high elongation called superplasticity, and the superplasticity is possible today, and titanium materials and many other very complex materials, you can produce superplastic components, and some of the components are shown here of titanium. So that's what I show here. Next, in the next 5 minutes, I think it's close to 5 o'clock already. Yes, and I will take next 5 minutes or 7 minutes, finish up my portion on the Konark iron beam. So the iron beams of Konark, so we have studied about now the high carbon material, and how from high carbon materials our ancestors succeeded in studying the microstructure and building up an optimum microstructure, produce the right properties in order to get excellent Damascus swords, which displayed extremely remarkable properties of retaining the edge and working in the battlefield for long times. And because they were high carbon, they were able to retain their edge. But people are wondering, if they are high carbon, how are they becoming ductile? Because they have to be long and they have to be ductile, so that because when you actually use them in the battlefield, they have to bend. So, etc., etc. So this is the beauty of the high carbon material produced in India and elsewhere, and Damascus swords are made. Now it's a very different kind of material when you are talking of the iron beams of Konark. But before I talk of the iron beams of Konark, naturally we will spend a minute on the what you call the Konark Temple itself. The Konark Temple itself basically Tagore, the great poet laureate, calls it, here the language of stone surpasses the language of man. So beautiful is the temple and the sculptures of the temple. So this is actually what you see here is merely the facade of the temple, not the full temple, because the temple doesn't exist anymore. What exists and people go to Konark to see today and call as Konark Temple is only this temple, which is only the Mukhsala. Mukhsala, the English word of that is facade. So this facade of the temple is the World Heritage Site since 1984. And as you all be knowing, it is the UNESCO which calls or actually calls the various sites as the World Heritage Site. For example, Ahmedabad was declared the World Heritage Site last year, and there are many, many World Heritage Sites in India. So there are natural heritage sites as well as artificial. Artificial is man-made. So Konark Temple, why was it erected? It was a unique temple for sun god worship, which is one of the most astounding temples. But this was built around 1250 AD. So, of course, the new way of expressing 1250 is not Anno Domini, but it is CE. CE stands for Common Era. BCE is nothing but BC. So, this is 1250, which means in terms of Delhi Iron Pillar, this came up roughly 800 years afterwards. And during the reigns of Eastern King Narasimhadev, who existed between 1238 and 1264, Konark Temple was built here, and the building of the Konark Temple took about 12 years. I will come to that a little later. This is just to show how beautiful the temple is. What you see in front of you are actually the entire temple was built as a concept of, or in the concept of a big chariot, and the chariot had 24 wheels, and these 24 wheels on which the chariot was actually mounted. And the sun god, or the god of sun, is supposed to move around on this chariot throughout the year. So all the 12 seasons are depicted, the 12 months are depicted, 6 seasons are depicted, and the 24 hours, which means the sun starts from the east and then sets in the west, which is why the sun temple in Konark, it was facing due east. And it is said that when the temple was erected, initially the temple was facing, of course, the east even today, but the sun's first rays used to reach the sanctum sanctorum, and there the myth goes that there was a huge metallic plate on which the sun's rays used to fall, and it used to shine. But look at this beautiful wheel. The wheel from ground level upwards, every inch of space is sculpted beautifully. This is what I would like to bring to your attention. And as a matter of fact, the history of Konark is, after the temple was built, or in order to build the temple, why was the temple built there? Why was the Sun Temple built on the coast of Bay of Bengal? And that place is known as Konark, or the seashore is known as Chandrabhaga, because that's where the river Chandrabhaga flew. Today, the Chandrabhaga river is primarily gone, in the sense that it is, you don't see anything. It is covered with sand, but a team from IIT Kharagpur, the team of geologists and humanities department, they have studied the course of the river Chandrabhaga, which is now fully covered with sand by ground penetrating radar, GPR. So we are not talking about the details that, but the most important thing is between 1250, when the temple was built, to 1750, when the temple collapsed and broke away. For these 500 years, the temple was existing. Where was it existing? It was existing on the coast of the Bay of Bengal. So this is actually the tourist map of Odisha, and you'll find Konark somewhere there. Just hold on. And Puri, if you can find. This is the Chilka Lake. So this is Puri. This place is Puri, and this place is Konark. So this is about 60 kilometers, Konark to Puri. And those of you who know Bhubaneswar is right here. This is Khurda, so Bhubaneswar is somewhere here. This is the capital of Odisha. I'm speaking to you from Bhubaneswar only. And this is the Bay of Bengal, and this is Konark, and this is Puri. And Konark used to be known as the Black Pagoda, and the Puri temple, Jaganath Temple, was known as the White Pagoda, because on the Konark Temple, a lot of the wild growth of trees had taken place. So the selling passengers from Europe, particularly the Dutch and the British, they used to see something on a mound. It was looking like dark, and therefore they were calling it the Black Pagoda. And whereas the temple in Puri, that was looking more like the shining temple, which is why it was known as White Pagoda. A word about the temple architecture of the Kalinga architecture. I think our friends should be interested in the Kalinga architecture. And now this is called the Kalinga style. What happens in the Kalinga style is all the this is called Rekha Deula. That means this is primarily a curved temple. There is a curvilinear smooth curve. This is why it is called Rekha. And below this, inside the temple, the sanctum sanctorum, or in Sanskrit we call it the Garbhagriha. So the Garbhagriha or the sanctum sanctorum or the main god used to be housed in the Rekha Deula or the temple. But just before that, you have a pyramidal structure. And this pyramidal structure is known as Piradiullah. And these yellow structures which are pyramidal, and no god or icons or goddesses used to be accommodated inside. It is only inside the Rekha Deula. In some of the temples in Odisha, only in Bhubaneswar, one temple actually, you will find what is called the Khakhara Deula. In the Khakhara Deula, it is not a sharp one, but it is almost like a parabolic nature on the curve. But this kind of nature of the temple you will find in South India, a number of them. But in Odisha, you will find this is the axis. The axis is west to east. So this is the east side, this side is the west side, and this one, the Khakhara Deula, is primarily for the tantric goddesses. So this is how the temples used to be imagined or built. So roughly in the Konark Temple, when the main temple was existing, the original temple was existing like this, which is the Sikhara, and this is the smooth curve, and in front of that is the facade, which is Jagamohana, and then of course here the Natya Mandira and so on used to exist. But the entire portion, which is this whitish part, is all broken, gone forever. And how tall that was is given here. How did you know that? Essentially because that there are many travelogues from which you learn. Also in Akbar's court, when the book was written by Akbar's court people, there the description of the Konark Temple has been given, and with its entire grandeur, the temple has been depicted, and that clearly shows that the temple was about 230 feet, roughly 70 meters tall. And remember that the Delhi Iron Pillar is roughly 16 meters. This is more than 70 meters. It was by far considered the tallest temple in the whole world. And the entire tallest temple is gone actually today. And what remains today is the Jagamohana, which is roughly 128 feet. And in front of that, the Natya Mandira. So if I come to the Jaganath Temple, Puri, because this is a temple many of you would know, you'll find the similar kind of thing. The two pyramidal structures in front. So the Natya Mandira is there, and then the facade is there, which is the Muksala or the Jagamohana, and the Rekha Deula. And this is one interesting aspect of the temple. In some parts of the temple, you'll find actually a giraffe. This is very interesting. How would you find a giraffe on a temple which is in Bhubaneswar or in Konark? Because giraffes are not natural habitats of India. So where are the giraffes coming from? So these are indicative of the fact that probably Kalinga, that's where Odisha's present name is this. But Kalinga was, of course, a much bigger area. Probably Kalinga essentially comprised present Odisha, present part of Andhra Pradesh, or what we call as the present Andhra Pradesh, and part of that maybe. And the Kalinga kings, people say they came from the south also, but they settled mostly in Puri and Khurda. And they had links, maritime links, so which is why we knew how a giraffe would look like, and that is how the giraffe. So the concept of Sun Temple as a chariot, this was conceived here as a massive temple. I have seen some of the Sun temples in Egypt. They are absolutely massive, much bigger than Konark Temple. They were built about 2,500 years back, but not anywhere as beautiful and as finely sculpted as the Konark Temple, which is why this was essentially given the tag of the World Heritage Site. So the concept of temple I have told, let me quickly go through this. The collapse of the main temple. Why did it take place? There are many theories, but some work which was done by IIT Kharagpur and CBRI, Central Building Research Institute in Roorkee together. I've seen some of the reports. Primarily it says that the foundation was somewhat faulty. Remember, the temple is located on the seashore where the soil itself is rather weak. And if the foundation therefore is not able to withstand the 230 feet temple, but remember it was standing for 500 years, but it is prone to gales, storms, tsunamis. But actually tsunami, we do not know whether it took place or not, but the super cyclone certainly must have taken place, and that is how it broke. It collapsed. When did it collapse? Around 1700 something. How did you know that? Because Aini Akbari, which was primarily a great treatise during the during the reign of the great king Akbar, and his courtier Abul Faisal, who was a great historian, has also written about it. Okay. So now, if you go to the Konark Temple today, if you look to your right, you'll find these iron beams. The iron beams have been collected. They were strewn all over. I must tell you here, 1750 or thereabout, the temple collapsed. We didn't have time actually to show to you the artist impression. Several artists who were British. They had they had actually visited the place when part of the Konark Temple was still existing, the main temple. But anyway, the whole thing collapsed, and the whole thing was under a debris. And it was around 1805 or 1807. Odisha was occupied by the British only in 1803. So by 1850, they discovered the Konark Temple. And part of that, up to the wheel level, it was all submerged under the ground. So therefore, they have to dig it up. And it took about 50 to 60 years. By 1905, they actually established the temple. And then they decided that whatever remains from the temple, from the facade, they must fill it up with sand. That is what actually happened. So today I must go back to this initial temple here and tell you, yes, this temple now, all these doors, this is the eastern door, this is the northern door, this is the southern door. All the doors have been closed now, sealed. And with the orders of the British government from the top, they filled it with sand in order to protect the roof so that the temple will not collapse. But today the time has come where the world body UNESCO is thinking of how to take the sand out and how to once again re-establish the facade or the entrance. Now, if you go to, you cannot enter the temple, but a gentleman, Mr. Bisen Sorup by name, he was a civil engineer who was transferred from Patna. He was brought to Konark, and he was asked by the British government to fill the sand part. So this is the door, but this is the doorway. On the doorway, you will still find the iron beams. So I found the iron beams here. And then I started looking into, I did some research on the iron beams. I found that the iron beams are all flat looking. The smooth surface on the top and all sides. But it struck me that there is something very interesting here. And in these interesting portions, protruding portions are there. As if these are embedded. I went through all the history books and there was no mention of this, how they were made. People said, yes, they were there. And then one or two history books, one by a British, one by one of the Odia historians, wrote in Odia, and they said that probably they poured liquid iron. But then liquid iron, as I mentioned to you, was never existing. So the method of manufacturing the beams was that smaller portions of the wrought iron or the Bloomery iron, 1 to 1.5 feet, they were placed side by side. They were placed one above the other, and then they made up this. Each one of them is about 11 inches. The diameter, not diameter, In the depth of that is about 11 inches, and the length is more than 30 feet, and some of them. And then the weight of each one is more than 7 tons. That's the, when I say more than 7 tons, each one of them, therefore, about 7 of them, they're taller than Delhi Iron Pillar. They're larger than Delhi Iron Pillar. These people do not know sometimes. Then I found something more. I found that they must have actually hammered it. The hammer signs are all there. If I look at these portions are all the hammering signs are there. Not only that, while hammering was done, why did they do the hammering? First of all, small pieces were laid side by side, one above the other. Then you pour the Bloomery iron, hot Bloomery iron once again, and then in a container. And then they started hammering it. When you start hammering it, you will produce one single beam, but inside the one single beam, there will be many smaller beams. That is why I called it a composite beam. And probably for the first time, a composite beam we discovered in Konark. This is very interesting. And one of the earlier persons, M.K. Ghosh, in the 60s from Tata Steel, he had taken a sample, done some work at the BE College, which is today the university in Calcutta, the North University. What is that called? Whatever, NIEST. What happened was, when he was trying to make a sample, suddenly there was a cleavage plane, and he found automatically the crack took place this way. And he didn't pay much attention. But all this happened essentially because inside the main beam, there are smaller portions, and it actually cracked there. And the microstructure of the beam, from the low carbon to high carbon, these are the low carbon material. Here there are high carbon, essentially because the beam is a long one. So they were bringing iron and making it there. The beams are being made. So the irons have different carbon content. They are being brought, and that is how it was being made. So the tensile properties, they were 300 megapascal. Remember, these iron beams, they were made essentially to carry the Navagraha. The Navagraha itself was more than 70 to 90 tons. The biggest Navagraha of Konark Temple. Massive, absolutely massive. And the British government wanted to take it to London. So they found it is impossible. They started taking it to Calcutta Museum. They dragged it, they wanted to drag it. They could not drag it even by an inch. And this, remember, the entire beam was lifted, not the beam was lifted, and so the stone was lifted, kept on the beam. That's what our ancestors did. And the British could not drag it. Then what they did was, from London, they brought a special machine, cut the stone into 3 pieces, and the portion where the Navagraha was actually sculpted, only that portion they dragged. They could drag it only 100 feet. They couldn't drag it beyond. Left it there. Today, if you go to Konark, you will find a beautiful museum surrounding the beam itself. And this is what has happened. Some portions have been rusted on the top because they are weathering. They are actually basically facing the rains and the sun throughout the year. So our aim, concluding observations are, this is only a preliminary presentation. We have actually submitted a big project to Government of India, to SHRI project of DST. SHRI standing for Science and Heritage Research in India. Hopefully, we will get that project, and between IIT Kharagpur and the CSR lab and myself, we will do the unique forge welding process. We will try to learn more about it. How many smaller pieces, for example, are there, and so on. By doing special ultrasonic work, we will come to know about it. And that's the end of my talk. Thank you very much.
Thank you so much, Omkar ji. It was a very, very enriching session. Thank you so much. With your permission, can we have some questions from?
Absolutely, absolutely. I'll be really delighted.
I think participants, if you have any questions, you can kindly raise them.
Maybe you have got some. No, I don't see any chat box questions.
Yeah. So if you have any questions, you could raise your hand, or you could type it in chat box. Yeah. We have a question from Kayal ji. If you could just unmute yourself.
Kayal ji, yeah. Dr. Kayal ji.
Yes, sir. Actually, it was
Kerala.
a wonderful. No, sir, I'm from Tamil Nadu, sir.
Tamil Nadu, wonderful.
Chennai. Sir, the session was really wonderful. I have just 2 questions, sir.
Yes.
One is that when you keep the iron in the iron particles in pyramid, it's not getting rusted. I just want to know the reason.
Yes.
And second thing is, I'm a biomedical engineer as such.
Yes.
So what kind of steel is biocompatible and can be used inside a human being? So these are the two questions which I wanted to ask.
Okay, the second question first, because that would not interest many other people. That's why I would like to take the second question first, the biocompatibility. So the biocompatibility, as you know, in the last 50 years, all the research that you do on the biocompatible materials in many parts of the country, I think we have one in Kerala, which is trying to make the heart machines, etc. Then IIT Kharagpur's biomedical engineering also. But by and large, it is your the direct answer to your question is 304, 18-8 stainless steels. They are more compatible with the human body. Stainless steel 304. But if I merely say the stainless steel, that will not answer your question. So it has to be stainless steel, and it has to be, you know, if people have done actually a rib, for example, a rib, or for example, let us say a bone in the leg is broken, and I am actually putting it as a replacement for a bone. And so therefore, what would I do? I'll take a stainless steel piece and then roll it, make it exactly of the same dimension, etc. Ensure that it does not have any residual stress by thermal processing, and then put it in the human body. So two things I have said. One is what is biocompatible in terms of composition. So that is the stainless steel. And then in terms of physical properties, it should not be stressed. So therefore, I have removed the stress by the thermal annealing, and then we have put it. Because if I put two pieces, for example, one is rolled, it has more stress, one is annealed, and if they're touching each other, this has happened in England about 20 years back. It became a big case also. So one annealed, one stressed, and they didn't know that they have not gone through the same processing, put it together somewhere in the rib, and the one which is annealed will survive, the one which is stressed, that got corroded, because that becomes more anodic in nature, chemistry-wise. Now answering your first question. Delhi iron pillar, I mentioned, of course, somewhere in my talk, that Delhi iron pillar for 1600 years, that didn't corrode, became rustless. Even the Konark iron beams, as you have seen, it has corroded only on the surface, but it has not corroded very much. So Dr. Kyle Vizzi's question was, what makes it rustless? So what makes it rustless? There are about at least 10 to 15 papers on that. I think the most important papers have been published by some of the Indian researchers. Amongst them, the most notable work is from IIT Kanpur by Professor Bala Subramaniam. We used to fondly call him Bala. But sadly, Bala Subramaniam died at the age of about 44, 45 of cancer. So Bala Subramaniam's work showed, now this is where the answer lies, that the beams of, not the beams, Delhi iron pillars, they contain more of phosphorus. Where did the phosphorus come from? The phosphorus actually, that is the kind of ore where the phosphorus is normally high. In all iron ores, the phosphorus is high, but again varying actually from about 0.1% to 0.5, 0.6%. And the iron making process that India adopted, we cannot remove phosphorus, and therefore the phosphorus remained. But when the phosphorus remains, it also imparts the corrosion resistant properties. But in addition to that, Bala Subramaniam's works, those are published in the British Corrosion Journal and the American Corrosion Journal, showed that there are amorphous layers also that forms during the processing. So A, because of the phosphide layer, and B, the amorphous layer, together they imparted the corrosion resistance or rustlessness. The most important question which you did not ask, but which actually emanates from her question, I must also say that. And Namrata ji, this is very interesting, because everyone will say, then why not the modern metallurgists of today make steel and iron with high phosphorus? when our ancestors knew how to make it rustless. She didn't ask it, but this is where it begs the question. So to that, the answer is, if I would be making a steel or iron with very high phosphorus, yes, they would probably become more corrosion resistant, but they will all become extremely brittle. The phosphorus goes into the grain boundaries and they will become brittle. So therefore, what happens is, while in Tata Steel and also in NML, we went through a very innovative process, patented also, that yes, we increased the phosphorus slightly. We call it phosphorus precipitation hardening and the solid solution hardening by phosphorus. I repeat, solid solution hardening by phosphorus, but ensuring that phosphorus doesn't go to the grain boundaries. How can you put atoms only in the grain boundaries and how do you know that? So today we have techniques. IIT Madras, for example, we have a 3D atom probe. In the 3D atom probe, someday, Dr. Kyle Vijay, if you go there, tell them that please show me your 3D atom probe. That's where we see where the atoms are going. So we add another element like niobium or like boron, which will actually precipitate in the grain boundaries, prevent the precipitation of phosphorus. So we would have added phosphorus, but prevented the migration of phosphorus to the grain boundary. So our ancestors know, they did not know this kind of technique. So they knew, they did not take the phosphorus out, but they did not know that by putting phosphorus, it will become brittle. Fortunately, this is something very important, that the Konark iron beams contain less phosphorus than the Delhi iron pillar. Number two, Delhi iron pillar is far away from the seashore, because Delhi is far away from seashore. But the Konark iron beam is hardly 3 kilometers from the seashore. So A, phosphorus is low, B, it is very close to the seashore, and C, it is experiencing rain and sun day after day. You will ask me, then Delhi iron pillar also is experiencing rain and sun. What is the difference? Remember, Delhi iron pillar, as the name says, is a pillar, and it is conical in nature, cylindrical actually, but slightly conical. So because it is standing there like that, it does not contain or accumulate water. But the beams are actually lying on the horizontal position. So that's the reason. So these are all the reasons why Konark iron pillar contains higher phosphorus than the modern day iron. So it is showing somewhat rustlessness, but it contains less phosphorus than Delhi iron pillar. So it shows more of rusting. It also shows more of rusting compared to Delhi iron pillar, because it is much closer to the seashore. Plus it is lying horizontally on the ground over the past 300 years. So it has collected more water. I'm sorry, I took a longer time in explaining. Yes.
Absolutely. No, sir. Every word of yours is so precious. I don't think, I think it's only enriching and really valuable for all of us. So actually, we have one more question as we speak.
No, Dr. Mansi Chaudhary.
Yeah.
Yes.
Sir, namaskar. It was really nice to hear you.
Sir, I'm not able to see you. Where are you?
Sir, my camera does not work properly.
Okay, doesn't matter. Your hand is showing. Yes, your palm is showing.
I have completed my PhD in this very subject, corrosion science. And it was under...
So your background is chemistry or chemical?
Yes, sir, chemistry, inorganic chemistry, sir.
Very good.
Sir,
where are you from, Pune?
Sir, Professor Gurmeet Singh. He is...
Aha! Oh, he's from IIT.
No, sir, from University of Delhi.
University of Delhi.
Yeah, so he's currently the Vice Chancellor of University of Pondicherry. You must be knowing him.
Oh, yes.
Yes, sir.
Nice, Vice Chancellor of Pondicherry.
Because you were talking about phosphorus, I just wanted to add that the compounds that I worked upon. So I have worked upon mitigation of corrosion of aluminium in the acidic medium using phosphonium compounds, and these are like, ionic liquids type of compounds. So I was just adding to it, and I was just not asking any question though. Thank you very much for your,
No. Very good that you have added. But kindly, all since you are basically inorganic chemistry background, go through the British Corrosion General, Bala Subramaniam's work.
Yes, sir, I have noted that down.
So you will find the complete crystallographic analysis of the amorphous layer and also the iron phosphate which is formed, etc., etc., and the combination of all that. So the whole world for the past 110 years, it has actually been researching only on this area. Do you know that today in Delhi Iron Pillar, at the foot of it, a small plaque has been placed by the American Society of Metals, ASM, as a matter of tribute, as a mark of tribute to the humanity or the Indian metallurgists who actually made it corrosion resistant. I didn't talk about it today, but that's very interesting.
Yes, it is really nice to hear from you. Thank you very much.
Thank you. I think people have, I think questions have dried out.
No, sir. I think we're all taking some time to really digest all of the information and knowledge that you've shared with us so beautifully. I'll also request if we have some more questions, we can reach out to you through, I will try and collate it and share it.
No, I will be glad to respond. I'm basically what you call male savvy person. So through you, let all the participants, whoever has any question, if they direct it to me, I'll be only glad to learn, because we don't know answers to all questions, but we'll be very happy to respond to some of them. Yes.
Absolutely, sir. Absolutely. Thank you so much. Thank you so much for this session, sir. It was really a very amazing session and very, very comprehensive learning experience for all of us. Thank you so much. Thank you.
Namaskar. All the best to all the participants. Namaskar.